Okay, and I think we can get started. So thanks everybody for coming. I'm happy to introduce our marine science seminar speaker, Sylvia D. from Rice University, where she's an assistant professor. She is an atmospheric modeler and works on climate science and paleoclimate. Her background from undergrad was civil and environmental engineering from Princeton. She did a PhD at the University of Southern California and postdocs at University of Texas and Brown University, and she's been at Rice since 2018 now. One of her big contributions so far is developing an atmospheric model that has water isotopes in it, and that's something that's actually very helpful for looking at paleoproxies. And she's been focusing on the recent past, the past 1,000 years or so. So today she's going to talk to us about longer timescales of El Nino, and let's all welcome Sylvia.
Thanks. So it's nice to meet you all. I'm sure I'll have an opportunity to see some of you in person in the future, but thanks very much for the invitation to visit virtually. And thanks for the introduction, Chris. So yeah, I did my PhD in LA, as Chris just mentioned, where we were constantly worried about drought and forest fires. And since moving to the Gulf Coast, we're obviously worried about very different climate impacts like hurricanes and floods. So I guess my early career has been permeated by an interest in extreme climate. And I know that, even in the past few months, my originally scheduled visit had to be moved because you all had major hurricanes come through your area. And I'm glad from talking to Chris earlier that hopefully everything has kind of calmed down and that you were all able to recover. But, I always think it's good to start with a 30,000 foot view. And we're seeing really active hurricane seasons and more intense rainfall. And, the cost of these events we know is going up. So this is a graph from NOAA just showing the total number of water-related billion-dollar events. Here in Houston, clearly we've had hundreds of billions of dollar events happening almost every year at this point. And we know the cost of the mitigation of those events is going up. And from a basic thermodynamic standpoint, we know that the warmer the atmosphere gets, the more likely these extreme precipitation events are going to become. And this is a picture from Hurricane Harvey, which was right before I moved to Houston, but I like to show it because this is sort of a famous intersection in our city. And I don't really know why this gentleman's smiling because as I mentioned, this storm was really costly. And then at the same time, we also know that particularly in Texas and in other areas around the Southern Great Plains, temperatures are projected to soar. We're looking at something like another month to 2 months of days over 100 degrees Fahrenheit by the middle of this century, which obviously has cascading impacts like drought and fire. And so given these stark impacts that climate change is already, filling our lives with, we obviously want to know how much worse these disasters are going to become. But answering this question is very non-trivial in our sciences because unlike our colleagues in biology and chemistry, we don't have an experimental mini Earth that we can put in a test tube and do active experiments on. So it would be nice if we had a little planet B to do all sorts of weird, geoengineering experiments, but we really don't. We just have our one planet. And so what we use are general circulation models. So climate models are sort of our next best thing that we can use to provide predictions of future climate changes. And so we can build these very complex models of the atmosphere and the ocean and run them forward in time or backwards in time and essentially use them like a very advanced video game simulation. And when we run climate models into the future, as I'm sure you're all aware, they predict pretty substantial warming as a function of how much carbon we emit to the atmosphere. So this figure is just showing the temperature anomaly relative to an 1800s base period. The black line here shows the total temperature change historically, about 1 degree Celsius. And then all of these additional lines show the warming that's predicted based on representative concentration pathways. So essentially, again, how much CO2 emissions we expect based on human behavior. And one of the things that's scary to me about this graph and to many other climate scientists is we have about 2 degrees Celsius of uncertainty on these predictions. And that's a wide range of uncertainty if we're talking about, trying to tie these back to extreme events. So the question is, what's driving this very widespread in climate model predictions? And if we break down that figure into all these little spaghetti lines, so this graph is just showing a different representation of the plot I showed before. So each one of these dark colored lines is the multi-climate model average of predictions of temperature change going through the 21st century. But then each one of these individual fainter colored lines is a single model simulation of the future. And you can see that there's considerable spread between what all the different climate models show for the future. And you can think about the different spread between these lines as two different types of uncertainty. One is the uncertainty in the external forcing. So between all these bold colored lines, that's the uncertainty in how humans will behave, how much carbon are we putting in the atmosphere. But between each color group, the spread between each individual faint line is the uncertainty in our understanding of internal variability in the climate system. So what do I mean by these two types of uncertainty? So we have external forcing. So these are things that happen to the climate system, changes in the amount of energy we get from the sun, changes in the amount of aerosol particles in the atmosphere, which reflect incoming solar radiation, or anthropogenic impacts like greenhouse gas forcing, excuse me. And then we also have drivers of climate variability that are internal. So these are the things that the climate system does all on its own. Things like the El Nino Southern Oscillation, the Pacific Decadal Oscillation, et cetera. And of these different rhythms of internal variability, the El Nino Southern Oscillation, or ENSO, is arguably one of the most influential and far-reaching modes of internal variability in the climate system. So the way that we represent both external forcing and internal variability in our models is part of what drives this large spread. So I'm going to focus just on the El Nino Southern Oscillation. For those who are unfamiliar with this mode of climate variability, it's essentially describing sloshing of a pool of warm water across the tropical Pacific Ocean. During El Nino conditions, we have very warm tropical Pacific Ocean temperatures. And during La Nina, conversely, we have colder tropical Pacific, specifically Eastern and Central Pacific temperatures. And these sea surface temperature anomalies are so large that they actually reorganize the entire tropical atmosphere around them. So essentially, we're just moving the locus of convection back and forth throughout the tropical Pacific. This warm water pool is really the heat engine of the tropics. And so one of the things that emerges as a result of ENSO is the Walker circulation in this figure. And so because of, again, just this change in sea surface temperatures, there's a big reorganization of weather and climate and the way that the atmosphere moves throughout the entire globe. So some of these teleconnections or impacts on weather and climate that occur far away are very well constrained. So we know there are characteristic rainfall patterns that occur during El Nino and La Nina events. So this map shows characteristic wintertime rainfall around the world during an El Nino event. We know that the southern US tends to be very wet, get very high rainfall across the tropical Pacific where everything's very hot. And then in other areas of the world, there's intense drying. So for example, during El Nino in Indonesia and Australia, where it's very dry, they tend to get big forest fire occurrence. And we also know that in Southern California, during big El Nino years, sometimes there have been big floods, landslides, et cetera. So suffice it to say that ENSO has these very large impacts on global weather and climate. So given that, we need to know, how will ENSO respond to external forcing? So how will the El Nino rainfall that we experience every 2 to 7 years be affected by things like greenhouse gas emissions? And in fact, this is one of the critically important, I think, but I'm biased, questions in climate science right now. And in the latest IPCC report, the finding was clear that we have high confidence that ENSO will continue into the future, but we have low confidence on exactly what will happen to it in the future. Is it going to get more intense? Is it going to oscillate around a mean that's shifting? We really don't know. And so coming back to this graph of uncertainties in climate models, there are two questions here. One is about internal variability, which is how will internal oscillators like ENSO interact with greenhouse gas forcing? And the other one is how will humans behave? And so for me, as a climate scientist, it's a lot easier to answer the question, how will modes of internal variability interact with external forcing? It's a lot harder for me to answer the question, how will humans behave? So I'm going to focus only on the former. So the question that will be consistent through my talk is, how can we reduce uncertainties in model projections that result from imposing external forcing on these very loud modes of internal variability? And as Chris mentioned, the way that I approach this is that I use changes in the past to contextualize or inform what might happen in the future, because the 20th century is relatively short. So we can use data from paleoclimate archives to extend our understanding thousands to tens of thousands of years into the past. So I'd like to tell you 3 very short common era or last 1,000-year vignettes about my research. The first one is about how volcanic aerosol forcing interacts with ENSO over the last millennium. The second vignette is about how tropical Pacific SST patterns affect rainfall in the United States. And then finally, I'll zero in on our region and talk about how ENSO interacts with flooding on the Mississippi River. So vignette number 1, let's dive in. So recall that my key question is really, how does external forcing impact ENSO? When a massive volcanic eruption occurs, sulfate aerosol particles penetrate the stratosphere such that we have reflection of incoming solar radiation, which briefly, for about 2 to 5 years, cools the climate system. And if we look back over the last 1,000 years, volcanic aerosols, big eruptions, are actually the largest thing, the largest hammer on the climate system over the past 1,000 years, until the Industrial Revolution, of course. And so these massive volcanic eruptions give an opportunity to test the climate system's sensitivity to these aerosol forcing events. Now, importantly, in almost all climate models, volcanism systematically influences the initiation of El Nino events. So it's been shown, in CMIP5 and also the Community Earth System model, that for the last millennium, whenever there's a massive enough volcanic eruption, we tend to see a tendency wow, that's almost the same word. We tend to see these very El Nino-like features in the tropical Pacific. And so the models can give us a prediction about how the tropical Pacific might respond to these changes in radiative imbalance. And again, it's very consistent against models. There's hundreds of papers on this topic. However, few people have actually gone into the paleoclimate record for the tropical Pacific to independently test what these models are showing. And so that's what we did. And we know that there are highly resolved, excellent documentation records from the tropical Pacific from corals that provide us an opportunity to validate these model results. So in particular, Palmyra Island, right here in this white dot, is smack dab in the center of action for ENSO activity. And we've shown in previous work that the oxygen isotopes recorded in coral skeletons have a very high correlation with the Nino 3.4 index. So we designed a hypothesis test to test the model results using these coral data. Our null hypothesis is that volcanoes result in an El Nino-like warming response, which is a model-generated hypothesis. The test is there any indication of a significant shift post-eruptions in these new coral data that we're generating? And as an extension, if there is a response in the coral data, how does it compare to the model simulations? So as a test of this null hypothesis, we took 320 years of new data from Palmyra, again, from these coral archives. And essentially, we can put these new coral data, which are monthly resolved, which is very hard to do, against the volcanic eruptions that have occurred over the last millennium. And importantly, the new data we generated for this particular paper overlaps critically with some of the biggest eruptions of the last millennium. So this figure is showing the oxygen isotope reconstruction against a reconstruction from ice cores of volcanic events. So this variable SAOD is stratospheric aerosol optical depth. And so each one of these blue sort of pinpricks here is showing a big volcanic eruption in the last millennium. And so you can see whenever the black line intersects with one of these eruptions, we have an opportunity to test this hypothesis. And in particular, the biggest eruption that occurred in the last millennium is in 1257 in Indonesia, and we have very strong coverage crossing that eruption. So if there is an El Nino-like response to volcanism, this very high fidelity paleoclimate record should capture that response. So we took the 6 biggest eruptions, we took the 20 biggest eruptions, we took the 6 biggest eruptions, and we plotted the coral data across all of those horizons. So each one of these gray lines here shows the volcanic event, and the black line here is showing the coral data. Take my word for it that for 4 out of 6 of these events, we do see a shift towards warmer or El Nino-like temperatures. However, this is a very small sample size. So how do we check for a statistically significant response to volcanism in the coral data? So to do this, we use superposed epoch analysis, which essentially is just a composite averaging technique where we take some of the data before and after the eruption, and we average it across all relevant eruptions to get a figure that looks something like this. So for every single data point above a certain eruption scale or threshold or size, we take all of the coral data intersecting that, and we can do a composite analysis and also do some uncertainty testing to see if the coral response is significant. So in all of the figures that follow, these red bars show the coral warming in response to the volcanic event, which happens at year 0, and the blue bars would show a cooling or a tendency towards La Nina-like conditions. So here's that test for 3 different sulfate loadings or sizes of eruptions. For smaller eruptions, we don't really see a significant response. These error bars here are showing a block bootstrap resampling and a 95% confidence level for us resampling across just all years where there was no eruption at all. So unless the coral data exceeds this bar, this could just be randomness. For bigger eruptions with a loading of 0.2 or so, the response grazes the error bars but doesn't exceed it. And then finally, for the biggest eruptions, there's no significant response. So the next question is, how does this compare to GCMs? So recall that we have multiple studies that report a very robust El Nino-like response to volcanic eruptions in the last millennium. So we did the same analysis. We used superposed epoch analysis on both the corals and a suite of model simulations. So this figure, again, is going from top to bottom, increasing the eruption size. Okay, so aerosol optical depth, A, B, C, D. And in colors here, I'm showing the Paleoclimate Model Intercomparison Project version 3 and also the community or system model simulations for the last millennium. Okay, so each colored line is the model response across these eruption horizons. And I'm using the same analysis that we just used for the corals. The coral data is in black, and those confidence intervals for the block bootstrap resampling are in light gray. So in every single one of these scenarios, no matter the eruption size, we can see right away that the model response to volcanism is much stronger than the corals. So if we just take this particular example, you can see that all of the CESM simulations show this very large response to volcanism that's almost 2, 3 times as large as the corals show. And furthermore, we also know that some of the models are getting really cold, some of the models are getting really hot. The disagreement amongst models seems to be a problematic feature here. And so what's the fact check of this model data comparison? The reason we're doing this at all is we want to understand if the model physics is wrong, what's going on. So a quick fact check. In the fossil corals, we see that the influence of volcanic forcing on El Nino events is not significant at the 95% level. There's still a possibility that El Nino-like responses are dependent on supermassive eruptions, which we just don't have any of in the last millennium. And maybe we need an even heavier hammer for a response to emerge out of the very large noise of natural variability that is ENSO. In the climate models, we see a very robust El Nino-like response to even mild or small volcanic events. So this begs the question, is the volcanic forcing overestimated? Is there wrong model sensitivity to aerosol forcing? Are there regional impacts that we're just not simulating well? So what is going on? I think there are about 3 different problems. So the first thing is that volcanic forcing is likely overestimated. My colleague and friend Andrea Burke had a really nice paper come out a couple years ago about how when you have these big eruptions, not all of the aerosols get into the stratosphere, but she developed a method to actually partition that based on the sulfur isotopes in these ice cores. And so we may be adding too much forcing to the models, which is causing them to overreact. The other problem is that our stratospheric transport in models is severely lacking. The way that we model sort of the way that stratospheric aerosols move from the tropics to the poles is really basic. And so there's been some really important work done in the last few years by Allegra Legrand at NASA GISS and others, showing that if we improve these stratospheric transport physics, we can actually get a much more muted response to volcanism in the models. So we have too much forcing and the models may be also overreacting. Now, the third thing that's really interesting about this is we're using these same models to simulate the atmosphere's response to geoengineering using sulfate aerosol forcing. So we know that there have been these solar radiation management schemes proposed to increase Earth's albedo by seeding clouds, emulating volcanoes. But we don't really have many natural experiments to check if the climate models are doing something correct in response to these point source aerosols. And so, paleoclimate data obviously only takes us so far, but in this case, we only have a few precious volcanic events to look at to see how the climate system, and particularly the tropical Pacific, respond to these radiative perturbations. And so if we're using models that are overreacting to sulfate aerosol forcing, the actual cost of geoengineering is probably going to be higher than we're actually estimating. So we asserted, and I assert, that it might be difficult to assess the uncertainties in these models, especially in terms of ENSO's response to volcanism. And we may have to double check how we understand how much these geoengineering schemes are going to cost. So just to close up this vignette, we find that the coral response to volcanism and the El Nino response to volcanism is insignificant, which contradicts many modeling studies. And El Nino events might be so strong that it might be immune to these climate perturbations like short-term volcanic cooling. It doesn't really care, it's going to come back. Current anthropogenic forcing, however, is about 3 watts per meter squared per year and growing. And so our results certainly do not discount the possibility of forced changes to ENSO due to sustained forcing over time in the future. And more importantly, there are proposed geoengineering schemes using sulfate aerosols to cool the climate, and they may have very uncertain impacts on the tropical Pacific. And until we understand these feedbacks better, we should probably understand the feedbacks better. I'll just leave it at that. Okay, so a little mental break as we transition to the second vignette. So the second study I wanted to tell you about has to do with how tropical Pacific patterns of change affect rainfall here in the United States. And how predictable is that rainfall, which is obviously, again, of high human importance. Our motivation for this study was that if we look at some of the last few big El Nino events that have occurred, we expected rainfall that never came. So when I was finishing up my PhD in LA in 2015, we were coming off one of the worst droughts in California's history. And then in 2016, all the climate scientists said, oh, El Nino is coming, everything will be fine. And then in 2016, we had a gigantic El Nino with no rain. So the question is, how reliable is the prediction that El Nino will cause flooding on the Mississippi or rain in California? Is it reliable at all? And so we can look at the average of rainfall during all of the El Nino events in the past, okay, so that we have instrumental data for, right? We know Southern California tends to be very wet, tend to get drier conditions in the Pacific Northwest. Same thing during La Nina, we get dry conditions in the US Southwest. And then if we look at 2016 and 2017, they almost look like the opposite impacts. We got La Nina-like conditions during an El Nino, and then we got huge rainfall the following year when the El Nino event was really coming down. And so this unreliability of rainfall during ENSO events means that it's difficult to predict. And that's a problem. The other issue is that we know that not all El Nino events are created equal. we know that the sea surface temperature patterns during different El Nino events is very dynamic and differs widely. So no two events are created equal. We know there are sea surface temperature anomalies that tend to be focused in the central Pacific or the eastern Pacific. And we call these ENSO flavors affectionately. And so what we're trying to answer now is there any rhyme or reason or predictability if we start focusing more on the spatial pattern of these events? So looking at 4 of the biggest El Nino events over the last several decades, so each of these maps shows sea surface temperature anomalies over the ocean in red and blue, and then over the continents, the moisture or rainfall anomalies in blue and brown. So, you know, turquoise colors mean it rains more, brown colors means it rains less. So keep your eye on California. So 1983, we have a massive El Nino event, huge amounts of rainfall on the whole West Coast. 1987, you know, if we were calculating the Nino 3-4 index, we'd get the same magnitude of event and there's no rain in California. 1998, very heavy rainfall in California. Again, same sea surface temperature anomalies in the Nino 3-4 box. And then finally 2007 as another example, totally dry. So the question here is, with so few El Nino events over the 20th century, how can we hope to increase our understanding of the predictability of rainfall over the US? How can we provide better statistics surrounding these ENSO-driven rainfall anomalies in the US? And to reduce these uncertainties, one needs a larger sample size. And so we can use paleoclimate data, and specifically paleoclimate data assimilation, to provide these expanded constraints on how sea surface temperature patterns and rainfall anomalies in the US are co-varying over time. So we're using new data products that were developed using a method called paleoclimate data assimilation. So if you've ever turned on the Weather Channel, right, you see these beautiful radar maps and projections of weather over the next 10 days. All of those numerical weather forecasting models are using data assimilation. They're taking data from radiosondes and satellites and feeding that into the weather prediction model. And in a similar way, we can actually do this in the paleoclimate realm as well. We can take tree rings and corals and ice cores, and in every year, we can assimilate that information into the climate model and tell the climate model, adjust so that you're closest match to these data for this year. So that's what paleoclimate data assimilation does. It essentially dynamically informs each snapshot of the atmosphere, and we have something that's physically consistent since we're using the dynamics in the climate model. So we're using these new products to give us a larger sample size of El Nino events. We're using the last millennium reanalysis, which was published several years ago, and looking at variables such as sea surface temperature, precipitation, geopotential height. We even have the Palmer Drought Severity Index in these data products. Over the last millennium, there are several key periods where we know climate was different from today. And so we use these 2 periods as a test case to understand how changes in tropical Pacific temperatures affect rainfall. So in this study, we used the medieval climate anomaly, which was from about 950 to 1250 CE, and the Little Ice Age, 1450 to 1850 CE. So we used these targets in the past, now with this full spatial grid afforded by the paleoclimate data assimilation, and asked the question, how do mean state changes in the tropical Pacific affect rainfall over the US? So the first thing we did was compare the sea surface temperature patterns in the tropical Pacific for these 2 periods to ask, okay, what are the mean state changes that we're working with so that we can assess its impact on rainfall? So this figure shows the sea surface temperature anomalies for the Little Ice Age minus the medieval climate anomaly. And we know from lots of the literature that the medieval climate anomaly is known to be a slightly cooler tropical Pacific mean state. We know that there were La Nina-like conditions during this period, a very dry Southwest. And so this map is just showing sort of the inverse of that. We're just showing a warmer tropical Pacific and a cooler tropical Pacific anomaly. So during the Little Ice Age, we have warmer central tropical and eastern tropical Pacific temperatures. Previous work has shown that when the tropical Pacific warms more in the east compared to the west, those teleconnections or those atmospheric waves will shift towards the east and dramatically alter rainfall in the United States. However, all of those studies have used climate model simulations and have been reporting these changes in the context of greenhouse gas forcing. So the question is that same pattern detectable over the last 1,000 years, and can we validate these future model projections? So the first thing we look at is changes in sea surface temperature variance. So this is the last millennium SST variance for the medieval climate anomaly and the LIA at the bottom, and the difference here on the right. And sure enough, if you just focus on the tropical Pacific, the difference in sea surface temperature variance from the LIA to the MCA shows enhanced sea surface temperature variance in the eastern tropical Pacific here, and reduced variance in the western tropical Pacific. There's small changes, but because the tropical Pacific's activities are so important to rainfall, we know that even these small changes can have big impacts on how we experience rainfall on the ground. So next we looked at the changes in rainfall accompanying these changes in sea surface temperatures. When we take the difference, again, between the warmer tropical Pacific mean state minus the colder tropical Pacific mean state, we get a pattern that looks like this for El Nino events. We see much more intensified rainfall over the Southwest US. And during La Nina, conversely, we see more intense drying. Drier US Southwest during La Nina, more rain in Southern California and the Southwest and Mexico during El Nino. And taken together, these changes are indicative of a stronger teleconnection. We have stronger El Nino rainfall, we have stronger drying during La Nina. We can zoom out for the full grid and see what's happening further afield in the tropical Pacific. And sure enough, for El Nino events, again, these are composite differences. We see this enhanced rainfall over the tropical Pacific. We see this nice wave train carrying additional moisture into the US Southwest, and the exact opposite thing happening during La Nina. So this just confirms that we seem to have this enhanced ENSO teleconnection during the Little Ice Age. So we want to know, what are the dynamics giving rise to this intensified teleconnection? What we think is happening is that the first thing that we know happened during the Little Ice Age is we have relatively warmer tropical Pacific temperatures. This influences precipitation, okay? We enhance precipitation. And we also see a negative geopotential height anomaly developing over the North Pacific and a high over most of North America. This is consistent with a southward deflected tropical jet stream, which would likely increase moisture delivery on the west coast of the US. So we think that if the central and eastern tropical Pacific warms during the Little Ice Age relative to the MCA, we're shifting those teleconnections eastward and actually strengthening them, especially over the Southwest US. And again, this jives with previous work investigating how rainfall is shifting in response to patterns of warming over the tropical Pacific. Now, a key sort of secondary question about this work is, what's more important for rainfall? Is it the sea surface temperature pattern, or is it the amplitude of what ENSO is doing? So historically, people have obsessed over the Niño 3-4 index and its variance over time. And people have also used rainfall strength in regions like the Southwest US that are very sensitive to El Nino events to reconstruct ENSO amplitude. So this is just one example from a study that was published in 2011, where they looked at tree ring widths during the same two periods, the Little Ice Age and the medieval climate anomaly, and they conclude, using teleconnected regions, tree ring widths, that ENSO variance, so that Niño 3-4 variance, was reduced during the MCA and increased during the Little Ice Age. And as I just mentioned, historically, these differences in the teleconnection rainfall have been ascribed to ENSO amplitude. So how literally how large is the standard deviation of sea surface temperatures in the tropical Pacific. So this study was limited to only having those tree ring widths. They don't have information from corals from the tropical Pacific. Because we have the full field now of sea surface temperatures coinciding with rainfall events, we can actually look at the ENSO amplitude, or that one standard deviation of the Nino indices. So here, again, I'm reproducing that studies. This is the North American Drought Atlas. And again, they show a strengthened teleconnection during the Little Ice Age in agreement with what we found. However, they're concluding that there was a larger amplitude of sea surface temperature variance during the LIA. We actually find that the opposite is true. There's actually a larger amplitude during the other period, or if we take any other Nino index, Nino 3, for example, there's no change in ENSO amplitude. And there's no significant difference between these two distributions in the LMR, the last millennium reanalysis. Okay, so the upshot here is there's no significant shift towards ENSO amplitude being larger, despite the fact that we have this stronger rainfall pattern during the Little Ice Age. And so what we think is crucial to point out here is that just changes in the pattern of warming in the tropical Pacific exerts a more dominant control on ENSO teleconnection rainfall. It's the way that the tropical Pacific warms that has a bigger impact on where it rains more. And it's a cautionary tale, I think, in interpreting teleconnected proxies like tree rings as a proxy for what's going on in the tropical Pacific, because the interactions between the way the Pacific is warming and where it rains and where it doesn't is much more complicated. So to conclude this vignette, we know that changes in the tropical Pacific patterns of temperature will alter teleconnection rainfall in the future, and we can see this happening in the past. So during the Little Ice Age, the tropical Pacific warms comparable to the medieval climate anomaly. The SST anomalies shift and strengthened during the Little Ice Age relative to the medieval climate anomaly. And interestingly, changes in future rainfall in many climate model simulations are similar, despite the fact that they have totally different external forcing. During the Little Ice Age and the medieval climate anomaly, we are pre-human intervention with the climate system. But we do see these mean state changes associated with the tropical Pacific. In the future, if we look at, for example, RCP 8.5 changes in SST, we see the same pattern of central and eastern tropical Pacific warming. We see an intensification of West Coast El Nino rainfall. And so I think this underscores the importance of reducing uncertainties in the pattern of global warming that the tropical Pacific is likely to experience, because that will give us more information about how rainfall will shift. So to conclude, the pattern of tropical Pacific SST anomalies affects the magnitude and extent of ENSO-driven rainfall, which should not be a surprise to anyone that studies ENSO, but it's the pattern that really matters. We think that the strength and the spatial expression of ENSO-driven rainfall can change independently of changes in ENSO variance. And this is relevant for the future as well, because in climate model, these multi-model simulations that we're looking at for the future, we're obsessing over the Nino 3-4 index and whether or not it's getting louder. And we should be looking at the full spatial field. And so I think characterizing changes in the pattern of these SST anomalies will give us more predictive power about how future rainfall might change. And we should be looking at the model spread in that pattern. And just to give a hat tip, I've got a grad student working with me right now, Shinue Luo, and she's doing some really cool stuff using machine learning to look at these different patterns over time and how they're associated with rainfall over different parts of the US. So hopefully she'll be able to talk more about this at a future AGU. Okay, so I'm almost done, but I think hopefully this last vignette will be of significant interest to everybody living in your part of the world, our part of the world really. And for this last part of my talk, I want to discuss some of the work I've been doing with collaborators on Mississippi flooding over the last 2,000 years or so. So I've been focusing sort of on the Southwest US, but if we once again look at the average of rainfall that occurs during El Nino, one of the bluest colors on the map is right in your region here. Okay, Louisiana, Mississippi, lower Mississippi Delta. And some studies have linked El Nino events to increased flooding on the Mississippi River. But there are so few events that have occurred, again, over the 20th century, where we have measurements that it's hard to say something conclusive or in a statistically significant way. So here, I'm showing the Mississippi River Basin in this map on the left. There are two stations here, Vicksburg and Memphis, where we're looking at river gauge data for the 20th century. So on the right here, I'm plotting changes in the Nino 3.4 index. So these are tropical Pacific sea surface temperatures. So these are our red and our blue colors. And then the gray and black shaded regions here are the height above the flood stage for four significant floods that have occurred on the Mississippi in the 20th century. So for 3 out of 4 of these cases, so 1927, 1973, 1983, we do see El Nino conditions preceding those floods, but 2011, not so much. And again, we're working with 4 events. So how do we get a better picture of how El Nino events are influencing Mississippi Basin hydrology? So for this project, we added more data points using climate model simulations spanning the last 1,000 years. So I'm using the same model I talked about earlier in my talk, the Community Earth System model. The last millennium ensemble actually has 10 different simulations, which go from 850 to 2005. So we took all of those simulations and we extracted the 1% of flooding events on the Mississippi using the river transport model. So CESM actually has a water routing system that directs all the water, towards major river systems on continents. And so we can use this discharge simulated by the model to try to look at the dynamical controls on elevated discharge throughout the basin. I use the same methodology that I described earlier, superposed epoch analysis, to look at several key climatic variables that have to do with flooding. So here on the x-axis, this is the time to peak discharge in months, okay? So 0 is the time of that top 1% flood event. And then here on the y-axis, we have soil moisture anomalies, precipitation anomalies, and that Nino 3.4 index. So you can see that on average, for the thousands of more floods that we now are simulating, we do see a correspondence between elevated sea surface temperatures, increasing precipitation, increasing soil moisture, preceding flooding events. And what we think is happening, what the model shows, is that there's a 2-phase regime where we have El Nino conditions gradually increasing precipitation over the basin, increased soil moisture, which primes the basin to be more prone to flooding. So there's a phase 1, 6 to 12 months before the flood, where we have this sort of slowly increasing rainfall over the basin. And then a phase 2, where we get this low pressure signal in the Gulf of Mexico, which leads to high precipitation events coming up through the Mississippi Basin. We can quantify the impact of ENSO on flooding in a more, statistically satisfying way. So here I'm showing the probability density functions as a function of peak annual discharge. Again, this is all in the model world for El Nino years in red and all other years in this gray and dotted line. And you can see that the probability distribution shifts towards much higher peak annual discharge by percentile during El Nino years. We can also explicitly plot up the recurrence intervals. So this would be the 2-year flood, the 100-year flood, the exceedance probability, and then again, the peak annual discharge. So for El Nino years, we can see that these recurrence intervals are shifted sort of to the right and down. And if you draw a line between 2 of these points, at the same percentile here of discharge, essentially what we're showing is that the 200-year flood becomes the 20-year flood during El Nino events. So there's a huge shift in the probability that we're going to get large flooding events over the basin if we have warm temperatures in the tropical Pacific. And this is sort of new, and my colleague at Northeastern, Sam Munoz, is really spearheading a lot of this work. In 2019, we had these big floods in the spring on the Missouri and Mississippi River. And if we look at the Nino 3-4 index preceding those springtime floods, we had a probable 6 to 7 months of lead time here, where we maybe could have said something to people on the ground, stakeholders, people that actually have control over flood infrastructure. And maybe some of the damage associated with that flooding could have been avoided. I think experts generally agree, people I've talked to, that these floods are the most damaging in 25 years. So there's this new generation of Mississippi floods that are occurring that don't really resemble floods of the past. And so the question now is, was this flooding predictable? And we're extending this work now by looking at discharge projections into the future. But now we have this understanding, at least in the climate model simulations, that El Nino really increases the likelihood of major floods. We know what the mechanisms are, and we can see how these different flooding regimes are reacting to what's going on in the tropical Pacific, for example, using these climate model simulations. So as I mentioned, now we're starting to evaluate simulations of discharge for the 21st century. We're trying to understand, some model simulations show enhanced evaporation, which would lead to drying throughout the basin. Some of them show this huge increase in extreme precipitation. So we're trying to tease apart which is going to win out. So just as a teaser, a postdoc working with me, Kieran Dunn at Rice, has been looking at sort of the peak over mean flows for historical gauge data versus what we're seeing in climate model projections using different amounts of CO2 forcing. So here in red, this is the RCP 8.5 business as usual, we do nothing. You can see discharge starts to increase exponentially. But then, here in blue, this is the medium we get our act together curve, and discharge remains much more stable. So there's a huge difference in how discharge reacts based on CO2 forcing. We also know that the discharge PDFs are really shifting again towards a much more enhanced peak flow state towards the end of the century. And we actually went through the project design flood for the Mississippi River and looked at how the return periods are shifting in these different CO2 forcing worlds. You can kind of ballpark draw these lines on where the project design flood is on these curves. And the bottom line of what we're finding is that climate projections are indicative of the fact that mitigation of carbon emissions could mean the difference between catastrophic failure of this flooding control infrastructure. And so that's something that we're still working on now. And it's obviously a can of worms. In the model, we don't have engineering. There's no engineering. So we're sort of just looking at what the climate system's doing, irrespective of what's going on in terms of the engineering on the ground. And so I think this project is exciting and has a lot of potential, but certainly requires a lot of input and collaboration from fluvial geomorphologists and engineers. So we're talking with collaborators at the Army Corps to try to move this forward, and hopefully we'll be successful. Okay, great. So just as a quick summary, my research broadly focuses on how the El Nino Southern Oscillation behaves. And we have several lessons that we can take away from the last millennium. In my first vignette, I talked about how climate models overestimate the volcanic response in the tropical Pacific. And we know that we need to probably improve the way that we simulate stratospheric transport. And these types of constraints are required for us to get a better understanding of how the tropical Pacific is going to respond to geoengineering, for example. In my second vignette, I talked about how the pattern of warming rather than ENSO variance matters more for how rainfall is likely to change in the future. So if we want to increase our predictive power for where it's going to rain more, where it's going to rain less, we should focus on what's happening in the full tropical Pacific under climate change scenarios. And then finally, El Nino increases the likelihood of major floods in the Mississippi in the basin. This is based on one model ensemble, but however, we do see evidence of this happening over the 20th century. The climate model allows us to evaluate the dynamics of how these floods occur with 11,000 years of simulated data, which is powerful for understanding the mechanisms. So thank you very much for your Zoom attention. And again, thanks for having me, and I'd be happy to talk through any questions you have.
Okay, thanks so much, Sylvia. A lot of really interesting results there. So I will help field questions now. You can raise your hand or type in the chat or just unmute and break in, but we have plenty of time for questions now. Stephen Howden?
Yeah, I really enjoyed your talk. It was really interesting, a lot to focus on. So I have some questions that maybe I missed something, but with the volcanic input and the tropical Pacific, were you just focusing on volcanoes that occur in the tropics, or is that volcanoes anywhere?
Yeah, thanks. I should have mentioned this. We only looked at tropical eruptions, so 20 south to 20 north. The climatic response to higher latitude eruptions is totally different. So all of those modeling studies I was talking about are specific to the tropical eruption response. There's a lot of work that's been done on how these modes of internal variability respond to like northern hemisphere eruptions as well, which is all really interesting work. But yeah, it's just, I think that it's tough. The way we simulate volcanoes and climate models is really primitive. And so I think it's good to keep comparing tree ring records and, other climate data from these sites, because in this case, we found that, people just tend to be living in their own little orbit. Like the modelers were like, well, this must be the way it works because all the models show it. And, then you've got a whole other community that is talking about the stratospheric transport being totally wrong. And so anyway, I'm digressing.
Do I have time for another question?
Sure.
So then onto the INSO patterns. So in your figure of the four major INSO events in recent times, where you were showing the SST and the rainfall, and I don't remember. So you were pointing out the differences in the precipitation in California for those different types of events.
Yeah.
Was the rainfall the same? Was it the same situation with the Mississippi River Basin area?
So let me just pull this figure up so we can take a look. So in fact, for all four of those events, arguably not 2007, but the rainfall patterns are much more consistent over the lower Mississippi.
Okay.
So this is also a really good and important question. It's like, well, are there areas that have more predictable rainfall impacts than others? In terms of California, it looks like there's a lot of variability, but the Southeast and the lower Mississippi seem to have more consistent responses to different types of El Nino events.
Right.
So this is something like my students working on now. If we wanted to make a regional map of where predictions of rainfall are more reliable versus less reliable, this is the type of stuff that people who work in, I guess, water management really want to know. And I've gotten questions from people who work in agriculture too. It's like, well, we need to know exactly what's going to happen. And it's almost impossible to do that, but it would help if we could say, well, it's probably more reliable than these other regions.
Is there, because you can see it, it looks like when you look at the index regions, it looks pretty the same in all four, but when you look outside the region, it's different. And so you were talking about using machine learning what about just simple like EOFs of the SST patterns and rainfall? Because it looks like what's happening, the index regions are
Yeah.
just not capturing that.
Yeah, so we've started doing the, I guess, the way that we classify Central Pacific and Eastern Pacific events does rely on EOF analysis. And so we're using that right now, like my students starting with that. You're absolutely right that many people would even label that as machine learning. Machine learning is this very broad, ridiculous term that, technically linear regression falls under. So uh, we're starting with just basic EOF analyses. Yeah. And I think we're looking at 3 key regions of the United States and looking at how those modes are, or I guess, the SST modes are changing rainfall over time. The machine learning piece, we would be using convolutional neural networks. And, we actually had a whole little discussion group a couple semesters ago at Rice about what do we really learn new about the physics of the climate system if we use these methods. And so, we can do the pattern recognition till we're blue in the face, but I'm not holding my breath in terms of if it's going to actually tell us something new that we can't learn from widely used, climate analysis methods that we've been using for, decades. So, yeah.
All right, thank you.
Okay,
Thanks.
yeah, I had a similar thought that, what are the prospects of, developing a new index that would be more useful for people? But yeah, it sounds like you guys are thinking about that. In the last few minutes, we'll go to Davin Wallace for a question.
Great, thanks very much. That was a great talk. I enjoyed it very much. Quick question: what kind of are your thoughts on the role that tropical cyclones play in some of the precipitation patterns? I know there's a strong connection with ENSO, of course, but I'm wondering what your thoughts are on that.
Oh, I mean, they obviously play a huge role, a huge role, right? I mean, this is one of the things I'm so excited about working with Lizzie, because she actually has all these model simulations of hurricane track. I mean, I haven't looked at this because climate models don't resolve hurricanes and tropical cyclones. And there are tons of people who are now running the model simulations and getting that data for the last millennium. And so I guess stay tuned, because we're going to start looking exactly at this question of sort of the frequency and intensity of tropical cyclones coming into the Gulf, just again in model world. But this work we're doing with ENSO is more about priming the basin to be sensitive to flooding. You do need that synoptic scale, big rainfall event to get floods, right? So I think that's the difference there. There's also, I mean, there's scary papers coming out now about marine heat waves and tropical cyclones. And certainly, I don't know if I'm the best person to be completing that type of work, but people who are doing paleotempestology and like tropical cyclone modeling, those are cool questions that they should look into, right?
Yeah, absolutely. And it's always, I've always obviously thought a lot about some of these connections, but it's interesting because there's ENSO as a driver for change in tropical cyclones, and then that could also have an influence. So it's this kind of strange chicken and egg snowball effect.
Right. And it's I mean, hopefully I'm not getting this backwards, but I think El Nino actually dampens hurricane activity.
Yep.
Right. And so
yeah,
the opposite influence there. And so it would be interesting to look at which one wins out.
Yeah. And I think you showed really nicely too that there's the kind of end members, of course, but maybe gradational ones in between. And that's kind of the gray area, so to speak, where there could be a strong, overprinting or, effect with some of these, components of the system.
Yeah. So the other thing is, like, my collaborator, Sam Munoz, he's been doing a lot of work too on the Atlantic Meridional Oscillation, because that has a much bigger impact on hurricane track. Like we've been looking at the position of the Bermuda High and like how that steers storms up into the Gulf. So there's a lot to deconvolve, certainly.
Okay, we are after 12, so we can close the formal seminar and send all your good vibes to Sylvia for a great talk. But she has a little more time, I think. So if anybody still wanted to ask a question, you're welcome to stay on the Zoom a little longer. All right.
Thank you. Thanks for coming.